Hello and welcome to this class. In this class, we are going to discuss verification of equations using dimensions. That means we are going to talk about how to verify physical equations using the dimensions of their physical quantities. In the previous class, we talked about fundamental and derived quantities, and we also discussed how to get the dimensions of derived quantities. So today we are going to be looking at different equations and see how we can use their dimensions to verify whether they are correct or not. It is possible to do that using the dimensions of the physical quantities in the equations. That is the focus of our class today. So if you have an equation like Ft equals mv minus mu, we can use the dimensions of this equation to verify whether the equation is correct or not. You can check the dimension of the physical quantities in this equation and use it to determine whether this equation is correct or not. If you have an equation like v square equals u square plus 2as, we can verify whether this equation is correct or not using their dimensions, the dimension of the physical quantities in this equation. This is very helpful if you are writing an exam and you are confused over an equation. You can quickly use this principle to verify whether the equation you have in mind is correct or not. So how do we do it? The steps. The steps in verifying whether an equation is correct or not are: the first step, the first thing for you to do is to list out the fundamental and derived quantities in the equation. List out the fundamental and derived quantities in the equation. So you look at the equation, then you'll find out which of the parameters is a fundamental physical quantity and which of the parameters is a derived physical quantities. You list them out separately. That is the first thing you do in verifying the equation. Then the second thing, or the second step you have to take, is to find the dimensions of the derived quantities in the equation. When you have listed out the fundamental and derived physical quantities in the equation, then the derived physical quantities, look for their dimension. That is the second step. Find the dimensions of the derived quantities in the equation. That is the second thing you have to do. Then the third thing you have to do is put together the fundamental physical quantity using their symbol, and then the dimension for the derived physical quantity. Put everything together and then compare to see if everything is the same. Coefficients in the equation are not to be taken into consideration. That means that you have to ignore every coefficient in the equation. Put together the fundamental and derived quantities, the dimensions, and then compare to see whether all of them are the same. If they are the same, then the equation is correct. If they are not the same, then the equation is not correct. Then I say that you should ignore every coefficient in the equation. Okay, example 1. If we have this equation ft equals mv minus mu, and we have to verify whether this equation is correct or not. How do we do it? Solution. The first step, to list out the fundamental and derived quantities in the equation. Ft equals mv minus mu. F represents force. Force is a derived quantity. T represents time. Time is a fundamental quantity. So have F derived quantity time fundamental quantity m is mass, it is a fundamental quantity, and v is velocity. This is final velocity and it is a derived quantity. Have m fundamental quantity and have v, which is a derived quantity, and then we have another m, which is fundamental quantity, and we have u, which is velocity but initial velocity. Okay, so we have another m, which is a derived quantity, and then u, which is, we have m, which is a fundamental quantity, and then we have u, which is a derived quantity. So the next step is to take the derived quantities and find their dimensions. So we are looking for the dimension of force, the dimension of velocity, that is the final velocity, and dimension of the initial velocity. Of course, two of them are the same thing, so the dimension for two of them is the same. We start with force. Force is equal to ma. This still has a fundamental quantity and a derived quantity. So we look for the dimension of acceleration, which is a. Acceleration is equal to displacement over time. It's talking about length or distance, which is represented with L as the symbol for the fundamental quantity, length. So we have length over time. Acceleration is velocity over time, Acceleration is velocity over time. Velocity itself is a derived quantity. So we find the dimension of velocity. The dimension of velocity is length over time. That is distance, and distance is length, it's part of length. The dimension, the symbol for length is L, capital L over time. So this alone represents the velocity. And so we have that acceleration now is equal to velocity, which is L over t, then over this t, so over t. So we put the symbol for the fundamental quantity here, capital T. And so we have that acceleration is equal to L over t. This is over 1. If we want to convert this division to multiplication, we invert this one. And so we have multiplied by 1 over t, which is equal to L over t squared. This is the dimension of acceleration. And so we put it together with the m, the mass here, to get the dimension for force. And so we have that force is equal to, the symbol for mass is capital M, then multiplied by L over t squared. So which is equal to ml over t squared. This is the dimension for force. Then we look for the dimension for velocity. Final velocity is equal to, velocity is length over time, like I've described before. So this is the dimension for the final velocity. It is the same thing with the dimension for initial velocity, length over time. So we've gotten the dimension for all the derived physical quantities in the equation, that of force, final velocity, and initial velocity. So we now put everything together and compare. We have Ft, force is, we got force as ml over t squared, ml over t squared, then it is Ft, then multiply by t. This alone represents F. Then this is for the t in the Ft. Then this is equal to mv. mv is L over t, then minus this is equal to m for mass and final velocity, then minus mass times initial velocity, the same thing. So this we have ml over t squared multiplied by t is equal to ml, m times l is ml over t minus ml over t. So we have ml over t minus ml over t. And so what we have is this, we have 2t here down and 1t up, so 1 cancel 1 here. Then we have ml over t, one t remaining down here, is equal to ml over t minus ml over t. So we see that everything is now the same. We have ml over t here, ml over t here, ml over t here. So the equation is correct. It's now verified. Example 2. Example 2. If you have an equation like v squared is equal to u squared plus 2as, and we are asked to verify this equation, then solution. We list out the fundamental and derived quantities in the equation. V is velocity, which is a derived quantity. U is velocity again, which is a derived quantity. Derived quantity. A is acceleration, which is a derived quantity. And then S is distance, which is length, is a fundamental quantity. Okay, so we find the dimensions of the derived quantities. The dimension of V is length over time. So we have length V square here is length over time squared. Then U squared, U is still the same thing as V. Both of them are talking about velocity. It's still length over time squared. Acceleration is the next one, the next derived quantity. Acceleration is length, that is velocity over time. Velocity alone, acceleration, velocity over time, where velocity alone is length over time. So we have that acceleration now okay, you have that velocity is equal to length over time. Now this means that acceleration now is length over time divided by time, which is LT. Sorry, if we want to change this division to multiplication, we invert this, and so we have L over T multiplied by 1 over T. So we have that acceleration is equal to L over T squared. L over T squared. Okay, so we put everything together now. Put the fundamental and derived quantity together. So we have L over T squared is equal to, that is for the final velocity, is equal to L over T squared, the initial velocity, plus 2as, we ignore 2, So we have, because it is the coefficients in this equation, every coefficient we ignore it. So plus AS, where A is L over, this is L over T squared, then L over T squared, then multiply by distance is L. So we now have L, this is L over T squared means L square over T squared. The same thing here, L square over T squared. And then here we have L times L, then over T squared. So we have L squared over T squared is equal to L squared over T squared is equal to L times L is L squared, sorry, plus L squared over T squared. So we now see that everything is now the same. We have L squared over T squared here, L squared over T squared here, L squared over T squared here. So the equation is verified. It is correct. Example 3. If we have ut is equal to s minus half at squared, and we are asked to verify this equation, how do we do it? We list out the derived and fundamental quantities. U is a derived quantity, T is a fundamental quantity. U derived, T fundamental, T fundamental quantity, S fundamental, that is for length, S fundamental quantity, S fundamental quantity, which represents time. So we have fundamental quantity here, and then acceleration is derived quantity. Acceleration derived, and then T is fundamental, T fundamental quantity. Now we find the dimension of the derived quantities. We start with U. U is L over T. U is velocity L over T. Then we have acceleration, that is the next derived quantity. Acceleration is L over T squared. We've gotten it before, that is velocity over time, which is L over T divided by T, which is L over T multiplied by T 1 over T multiplied by 1 over T, which is L over T squared. Okay, so having gotten this, we now put the derived and fundamental quantities together and compare the dimensions. So we have u is L over T multiplied by time is equal to S, which is length, minus half is a coefficient here, so we ignore it and move to T. T is L over T squared. Then this multiplied by T squared, multiplied by T squared. This means this cancel this, then T here cancel T here, and so we have only L here is equal to L minus L remaining here. So we have the same here, the same thing here, the same thing here, and the same thing here. So the equation is verified. It is correct. So this is how to verify physical equations using dimensions. We first of all list out the fundamental and derived quantities, and then we find the dimensions of the derived quantities. And the next thing is to compare the dimensions and then ignore coefficients.